All right, lesson 3. Let's make a switch. So, lesson 1, we learned all about acids and bases and what it means to be a weak acid and base. Then we kind of focused on the strong acids and bases for all of lesson 2. And then in lesson 3, we're going to come back to that concept of weak acids and bases and do some calculations. Now, the key thing here is that weak acids and bases do not completely dissociate in water, which means we can't say that if we know the concentration of the acid, we know the concentration of hydrogen, right? They do not completely ionize. So we're going to have to take that into consideration because they are going to instead establish an equilibrium between the reactants and the products. And we know as soon as we reach an equilibrium, we're talking about an equilibrium constant. So the equilibrium constant is going to describe how much dissociation occurs. Now, instead of using KEQ, we like to use our own constant. So in Unit 3, we used KSP for the solubility product constant. And in Unit 4, we're going to use Ka, which is the acid ionization constant, and Kb, which is the base ionization constant. Now, what these things measure is the ability of an acid to donate a proton. Or another way of thinking about this is how many hydrogens would end up in solution. So if you think of something like a hydrochloric acid, which I'm going to talk about in a second, but hydrochloric acid goes to hydrogen and chloride, and it goes whatever, if you have a 0.5 molar hydrochloric acid, you have a 0.5 molar hydrogen in solution. But when we're talking about a weak acid like a hydrofluoric acid, it's going to be different than this. It's going to be something more like the equation of HF plus water goes to hydronium and fluoride, or in simplified, just hydrofluoric acid goes to hydrogen and fluoride. But if we're going to write the Ka expression, it's going to be the amount of ions in solution, because it's not going to be a one-to-one. We're going to question how much it is. So what it'll be is you'll have something like a 0.5 molar hydrofluoric acid that you add, but you don't know how many hydrogens are in solution. So what would we do for the Ka expression? Well, the Ka expression is the same as doing KEQ or KSP, where it's the concentration of the products over the concentration of the reactants. So let's go for the acid ionization reaction in water. So in this case, it would be the hydronium ions in the products times the fluoride ions. And then in my reactants, I would include the HF. But do I include the water? What do you notice about the water? The water is a liquid, so we never include water, which is why I actually prefer, when I'm writing any kind of an equation for like math work, I always use the simplified version, because then it's easier to remember that water is not included. So in the simplified version, it would be the hydrogen ions times the fluoride ions divided by that hydrofluoric acid concentration. Okay, so both of those are Ka expressions. I say that you can use hydronium and hydrogen interchangeably. I do find the simplified version easier because then you remember not to include water in your Ka. So what does a Ka mean? Well, it's the ability of the hydrogen or the hydrofluoric acid or your acid to donate a proton. If you have a large Ka, it means that you've dissociated to a larger extent, right? To have a large Ka, you would have to have increased products and decreased reactants, right? Meaning that it would be a stronger acid. Whereas a smaller Ka means that you would have less products and more reactants is going to make it a smaller number, which means that it is a weaker acid. It would have less ability to donate a proton. So a larger Ka means the acid produces more hydrogen ions in solution. It is a stronger ability to donate a hydrogen, right? Or hydronium, whichever way you're thinking about it. So let's practice this from scratch. Let's write the Ka expression for the reaction in which, I don't even know what that is, HC2O4 minus acts as an acid with water. Now, if we're wondering what it is, don't forget that you can always go to your formula sheet, which I should probably have open in a separate tab, but I'm just going to go down. Oh, there it is. So it is hydrogen oxalate ion. So if I was looking for how this goes, actually, let's open that tab. 1 second. Okay, there we go. So I've got this open. The HC2O4 minus is right here. So this is the hydrogen oxalate ion. And if I look at its ionization equation, right? So HC2O4 minus goes to hydrogen ions and C2O4 minus. They use the simplified version because it is so much easier to work with. So let's do HC2O4 minus goes to, now we're using equilibrium expressions because this is a weaker acid, and it is going to produce hydrogen ions and C2O4 2 minus ions. Again, that is the simplified version, but that's really all we need. And so the Ka expression would be the concentration of hydrogen, which you could replace with hydronium if needed, or if it was a multiple choice question, you could recognize it, right? Times the C2O4 2 minus, because it lost a hydrogen, so it got one more negative charge, divided by this, what was it called again? Hydrogen oxalate ion. Hydrogen oxalate. Oh, I gave up. That's a 4. Ion. So that is my value of Ka, or that is my Ka expression. Okay. So now we are eventually going to start using the Kas that are listed on the side of this table, but for now we're just talking theoretically. If I asked you which solution contains the greater concentration of hydronium ions, something that has a Ka of 6.5 times 10 to the negative 5, or something that has a Ka of 7.8 times 10 to the negative 10, which of these solutions would contain the greater concentration of hydronium? So we don't have the Ka expressions, you just have to understand what these things mean. This is a larger value, which means the acid was stronger, so it dissociated into a greater concentration of hydronium ions. So greater concentration of hydronium ions. Right? The larger it is, the more products you have, the more that acid dissociated. Okay, so let's try a base ionization, so a Kb. An example of a base is a fluoride ion. Now, as I was mentioning in a previous video, this is fluoride. And if you tried to break up fluoride into a hydroxide ion, starting as a fluoride, you wouldn't get anywhere. These are the ones versus the metal hydroxides, which are strong bases. But most of these bases you actually have to put in water in order for it to see that it is forming that hydroxide ion and HF, right? So think about the fact that this is the base, this is its conjugate acid, and then you would have hydroxide, which would be the conjugate base of this acid. So this would be your base. This is your acid, this is your conjugate acid, and this is your conjugate base. Now, if you look on your information booklet and you tried to use fluoride ion in your simplified, that would be this guy, and it's not going to work. F minus plus H plus goes to HF. That's not going to give you it acting as a base. I mean, it does. It shows you accepting the hydrogen, but it doesn't include the hydroxide. So whenever I do weak bases, I always put them in water. But when I write the Kb expression, it's going to be the concentration of HF times the concentration of hydroxide over the concentration of that fluoride ion, but you never include water because it's just where you get that hydrogen ion from for the F minus to become the base. But then the key thing is that you're producing hydroxide ions in solution. So what's the meaning of Kb? Well, it's very similar to Ka. The larger the Kb, the stronger the base, the more ability it has to accept hydrogen ions, and the smaller the Kb, the weaker the base. The less ability of it to accept hydrogen ions and form hydroxide ions in solution. So a larger Kb means the base produces more hydroxides, which you will not see if you do not add the water in. So acids, you can go simplified. Bases, you cannot, especially not weak bases. Strong bases, sometimes you can. So if I wanted to write the Kb expression for the reaction of C2O4 2- acting as a base with water, I'm going to write C2O4 2- in water is going to form the conjugate acid HC2O4-, and remember I can use my equilibrium arrow, plus hydroxide ions. So that the Kb expression would be HC2O4- times the concentration of hydroxide all over the concentration of C2O4 2-. Awesome. So then just a basic theory question, which solution contains the greater concentration of hydroxide? It's going to be the larger Kb. So same idea, larger Kb, more hydroxide ions in solution. Right? Greater ability to accept the hydrogen from water, more production of hydroxide ions. Okay. So just a comparison, when you're looking at the chart, what I want you to notice is that all of your weak acids have a Ka value. We'll talk about Kb in a bit, but all of my weak acids have a Ka, and all of my strong acids, they just say very large. And down here, it just says very small. So what does that mean? Well, what it means is that when you have a strong acid, because strong acids dissociate nearly 100%, the Ka value is huge because you can essentially say that this is like going towards zero. Now it can't be zero because that would be undefined, but if you're dividing by a very small concentration, then you're mainly all ions in solution. And so the Ka would be very large, but it would be dependent upon what concentration of acid you're starting with and what concentration of ions you have in solution. And then same thing with Kb. Because the strong bases react almost completely with water, the Kb is also very large. You would be mainly ions, and this would be approaching zero. Awesome. Okay, so let's go practice some of those questions.